Guys, now please type, is the video working now? So please type in the chat box, is the audio and video fine now? Yeah, good evening guys, but please confirm the audio and video. Is the video and audio fine? Yeah. Oh. Just a second. Fine. Okay, thank God. Okay, great. There was actually some issue with the the internal software, I guess. Streaming was not able to. Yeah, but it's fine now, right? Good. Because I started 7 PM and I started teaching, and you are not able to see the live actually. Okay, but it's fine now. Okay. So anyway, today is the second lecture of this basically this single variable calculus. Okay, so we have started single variable calculus in the last lecture, of course, and we'll continue with the concept of limit differentiation. And in last class, I have explained you the concepts of limit, continuity, and differentiability. Okay, so how to check whether a function is differentiable or not at a particular point, I have told you. And also I have told you how to calculate limit of a function at a particular point, and of course the definition of limit, and also how to check the continuity or the smoothness in the function. Okay, now in of course, before going for today's class, if you see, these are the Telegram channels. This is for the Wallah English channel, and this is my personal Telegram channel, of course. So all updates regarding anything on this happening on this YouTube channel will be posted here, so you can join this. And at the same time, any update from me personally could be available here, so you can scan this and just enter this group, of course. Okay, and also please install this Unity feature so that you can have allocation of all your content at one place. And to just participate in this, before typing the doubt, please type the exclamation doubt and then start typing your doubt. Similarly here, keep exclamation note and then keep the note. Then these notes and polls, everything gets stored in the Unity space so that you can refer to them at later stages. Okay, and in the last lecture we were talking about the concept of limit, then continuity, and also differentiability. Okay, we have seen the first principle of differentiation. So differentiability of a function. Okay, so we have seen what is the physical meaning of a slope. Okay, so if you differentiate a function and if you put some value of x, you'll get some number. Okay, some real number, so or maybe some complex number depending on the limits being complex at the same time. So you can identify what to which value the function actually goes. Okay, and at a point, if you draw a tangent, the slope of the tangent with x-axis is nothing but the derivative value at that particular point. Okay, and as point changes, the slope of the tangent changes because the tangent orientation depends on the function again. Okay, so these are the things we have done, and of course I have given you some homework. Okay, so this is one homework question which I have given you based on your some basic knowledge. Okay, and this is also a previous year gate question. So if some of you might have solved this answer into the type, okay, the value of t, I'm giving you 30 seconds, you can enter the answer clearly. Okay, so this question I have given you as homework, and this is simply based on your prerequisite knowledge. Okay, just knowing some basic differentiation, okay, formula, that's it. So if you have solved this question, please enter the answer. The function f of x is equal to x into sin x satisfies the following equation: f double dash of x plus f of x plus t cos x is equal to 0. The value of t is dash. Nobody solved this question? Okay, so let's see. Anyway, if you want to solve this question, of course, so let's see. You have f of x is equal to x into sin x, correct? So ultimately you want to calculate the value of t, of course. Okay, and you all know this formula. If there is product of two functions, again of course I'll give in today's class, but normally you know how to differentiate product of two functions, right? First function into derivative of second plus derivative of first into second. So this implies your f dash of x is equal to first function into derivative of cos sin is cos x, derivative of cos sin x is cos x, plus derivative of the first function into second function as it is. Okay, so this is what you get. So x cos x plus sin x is what you have. This is f of x, f dash of x. So second derivative, if you differentiate this once again with respect to x, now differentiation can be split at arithmetic operators like plus. Now you can see product of again two functions. First function into derivative of cos x is sin x plus derivative of first function into second function plus derivative of second function, this sin x, which is cos x, of course. So this gives you minus x sin x plus 2 cos x. This is what you have. Okay, so this is f double dash of x. Now it is given that f given given f double dash of x plus f of x plus t cos x is equal to 0, correct? So let's see what is f double dash of x minus x sin x plus 2 cos x plus f of x. F of x is actually x sin x plus t times cos x is equal to 0. Okay, then you can see this x sin x and this x sin x cancels each other. Then t plus 2 times cos x is equal to 0 always. But you know cos x is not 0 all the time, depends on x. But this coefficient has to be 0. So therefore t plus 2 has to be 0. So t is equal to minus 2 of course. Okay, so t is minus 2 is what you get actually. Clear to all of you? It's just based on the product of two differentiate, basically derivating product of two functions, and you have to know derivative of cos is minus sign and derivative of sin is cos. That's it. Okay, you have to know these things. Clear to all of you? Yes. So can you all understand this? It's a simple some 2-3 couple of steps. That's it. But of course a simple job actually. Okay, you have a function which is you have basically product of two functions and you have to differentiate this. That's all. Okay. Bhavat, Sagnika, Ajay, Alex, Labi, Naid, Hemant, every one of you. Please type in the chat box. Is this clear to all of you or not? Okay, t equal to minus 2. Fine. So the answer is of course minus 2 actually. So of course negative you cannot enter, I guess. So anyway, if you just check it with some data, this is what t is equal to minus 2. So I got 817 gate score thanks to Gate Wallah. Yeah, okay. Welcome John Wick. Wish you all best. So let's go to the next question. Of course, anyway, I'll teach this. I have given this question. If some of you can solve, you might have solved this. But anyway, if you can't solve, we'll see in today's class how to solve these kind of questions, of course. Okay, so we'll get back to this question. So in today's class, basically, I'll continue graphs. First of all, we were drawing some graphs actually. Okay, so we'll continue that graphs. Then I'll talk about some standard derivatives. Okay, so some standard derivatives functions is what we will give. Okay, and limits and also mean value theorems is what we will see, of course, in today's class. Okay, so I told you in the last lecture, after dealing with graphs and some standard derivatives, we'll again visit back limits. Okay, because there is something called L'Hospital rule. Okay, so when you see this L'Hospital rule, then ultimately you'll have to apply some derivatives. So to apply those derivatives, you should know what are the derivatives of different functions ultimately. So that we'll look it up, and also we'll look at mean value theorems towards the end of the lecture today. Okay, so let's see some standard derivatives. Before going for some standard derivatives, I would like to continue the graphs. Okay, so in yesterday's class, I've given you graphs of sin x and also tan x and log x. Okay, so these are the things I've given. So fourth graph, continuation of graphs. Okay, I'll put a heading maybe continuation of graphs. Continuation of graphs is what I want to tell you. First, some basic graphs, and then so let's see. Fourth, because 3 I have given you, including log x, e power x. So exponential of x, of course. Okay, so how we get this exponential of x? You know, this is the function. This is y-axis, origin, x, y, and since e is positive, you know, this power function is always positive because base is positive. E equal to e power x is what you are plotting. So e is around like 2.718, of course. Okay, so approximately, and you have more decimals. And if you want the exact value of e, you can see, sorry, this is the gate calculator. So if you click on this e, okay, this e will actually give you this exponent value 2.71828. We'll see due course after seeing Taylor series how we got 2.718. Okay, okay, yeah. So let's see here. If you plot this e power x function, the graph that you'll have is this tends from minus infinity. So at x equal to minus infinity, this function value is always 0, almost 0, and you can see the function keeps increasing. Okay, so the function keeps increasing. Okay, this is what you have, and clearly you can see this value is 1, of course. Okay, and as x tends to minus infinity, this value tends to 0. So this is y is equal to e power x. E value is positive, something more than 1. So as this power increases, ultimately the value of the function also increases. Now coming to fifth graph, y equal to e power minus x. No, y is equal to e power minus x. Then ultimately it will be the reflection of this. Okay, so you can see, so this is y equal to e power minus x. Then what are the positive values of x got here? The same will come here for negative values because this one more minus is there. So you can see the graph will actually come something like this. Okay, so you can see it's exponentially decreasing, and this is origin, of course, this is x, this is y, and this is y is equal to e to the power minus x, of course. Clear? So because as x increases, the function value keeps decreasing, okay, ultimately because e is positive. So these are graphs you might have seen. Now let us see the graph of mod x also once before we move to other graphs. Y is equal to mod x, and we know this function is defined in such a way. This implies y is equal to x for x greater than or equal to 0, x minus x if x is less than 0. So if you plot these two lines, let's see what you'll get. This is one line, of course, x axis, and this is y axis, of course. Clear? So origin, x and y. Now clearly you know this mod x function is always positive for any value of x. Okay, now when x is greater than, so what's the meaning of symmetric in previous lecture? The graph looks similar on both sides of the x axis. Like for example y axis, like if you see, for example, I was teaching you one graph in the day 1. Okay, so if you see this is symmetric. Of course my drawing is very bad, but let's say if you have a circle like this, okay, then this if you take a function about y axis, it looks the same on both the sides. Okay, that's what symmetry means. Clear? Yeah, good evening, be on time. Okay, you should be on time always. Now let's see here. If you check the line, this graph, whenever x is positive or x is starting from 0, this curve is y equal to x, and you know the line y equal to x is something like this. Okay, this is y equal to x, of course. And when x is negative, x is less than 0, then y is equal to minus x, and the line y equal to minus x starts something like this. Okay, so y equal to minus x is like this. This is y is equal to minus x. So this yellow part is the graph of mod x. And in last class you have observed the value of basically the differentiation of mod x at x equal to 0 does not exist. Okay, means basically at x equal to 0 this function is not differentiable. I'm telling you, at any function, okay, or for any function, if it's getting a sharp edge, okay, or a sharp edge at any point, at those sharp points the function is not differentiable. Like here you see there is a sharp edge here. Okay, so at this sharp edge the function is not differentiable, of course. Clear? And you can see in last class we have seen limit f for f of x is equal to mod x, d by dx of this function at x is equal to 0, at x is equal to 0 does not exist. We have seen this. Okay, because we have observed one thing, left hand derivative limit h tends to 0 or x tends to 0 minus mod x minus mod 0 divided by x minus 0, which is equal to limit x tends to 0 mod x. When you have converted depending on positive or negative, x tends to 0 minus means x is less than 0, so x is negative, so mod x becomes minus x divided by x ultimately, so this is minus 1, of course. Okay, and similarly you have seen right hand derivative. If you calculate this right hand derivative value, limit x tends to 0 plus mod x minus mod 0 by x minus 0, so this gives you limit x tends to 0 x by x, this is 1. And since you have seen, this implies left hand derivative is not equal to right hand derivative, of course, so therefore at x is equal to 0, d by dx of mod x does not exist. Okay, so you have seen this. Now clearly this is what we have done in yesterday's class. Now from graph, if you observe, you can observe one point very clearly from the graph. When x is tending to 0 plus means somewhere in this region, so let's say x is tending to 0 plus means this is 0, say 1 is somewhere here, so within 0 plus the slope of the graph is plus 1, correct? Because when x is slightly more than 0, the function is y is equal to x, and you know y equal to mx. In this equation, the equation of straight line passing through horizon, m is the slope, of course. Okay, so this value is 1 on the right side because this is the line y equal to x, so in the right interval this slope is 1, which is exactly what you got here. Okay, after calculating the derivative at right in the right hand side, so right hand derivative value is equal to 1, of course. Okay, now let's see on the left interval when x is tending to 0 minus means in the left space this function is y equal to minus x, so slope value is minus 1. That's what you got, left hand derivative is equal to minus 1, and clearly these two derivatives are not equal, so ultimately the function is not differentiable at the point x is equal to 0. Clear? Is this clear or not? On the right hand side, if you draw a tangent, and in the left hand side, if you draw a tangent, the slopes of the tangents are not equal, so the derivative does not exist, of course, at that point. Graphically, that's what you can see for mod x. Okay? Is this clear or not? Even though the function is continuous, see, if you want, you can draw a tangent exactly at x equal to 0, but towards the right and towards the left, the values are something different. Okay, they're not equal. Okay? That's why the function is not differentiable at x is equal to 0, of course. Okay, now let's go to other graphs. This is 7, so 6, so 7. Let's say y is equal to what function we can take? Okay, so y is equal to maybe x into sin x, let's take. Okay, so x into sin x. Clear? So y is equal to x into sin x. Now how do we plot this graph? Of course, so let's see. First of all, you develop the coordinate system. We'll see how to plot this. Clear? So let's see how to plot this origin x y, which is of course x into sin x. Now let us observe one thing here. Ultimately, you know, we have -1 less than or equal to sin x less than or equal to 1, of course. Okay, so you know this. So -1 less than or equal to sin x less than or equal to 1. So this implies minus x, if you multiply x on this inequality, x into sin x less than or equal to x. This is what you get. Okay, means this function x into sin x always lies between minus x and plus x. Correct? So how can we draw a tangent at this point? X-axis itself is the origin. Okay, sorry, x-axis itself is the tangent to that curve. How can we draw a tangent as it's a point on the origin? See, on the origin, it's almost, see, it's a curve. Okay, obviously every point will be on that curve. So similarly, origin is also one of the point on that curve. That's it. Okay, like for example, if you have a curve like this, then ultimately at this point it's only a point. Okay, one single point, but you will draw a tangent to that curve similarly, but in that case it's a sharp edge. Clear? Now let's see. If you plot this, one thing that you understood is, in the first point that I told you, if you want to plot any graph, you should check for the ultimate values of the function. Okay, means the maximum value and the minimum value. Now if you take this x into sin x, this x into sin x function is bounded by the values of minus x and plus x. Okay, so we can do one thing. First, let us plot the lines y equal to x and y equal to minus x. Okay, so let's plot the lines y equal to x first. This is y is equal to x. Okay, and y equal to minus x also let's plot. This is y is equal to minus x, let's say. Clear? So this is y is equal to x and this is y is equal to minus x, of course. Okay, this is the lines. Now because of this understanding, whatever the shape you draw doesn't matter, that shape will definitely lie in between these two lines. Similarly, it lies in between these two lines, correct? Because it cannot go out into this region or into this region. So we have confined some space such that within that space only we have to draw the graph because of that inequality. Okay, now let's see. If you look at the nature of sine, sine is repeating. Okay, so when sine is repeating, let's say whatever might be the value of x, whenever you put x equal to multiple of pi, 2 pi, 3 pi, at all these values the value is 0, because pi into sin pi, 2 pi into sin 2 pi, 3 pi into sin 3 pi. So at all integral values the value becomes 0. Means if you, for example, plot the values like x equal to pi. Okay, so let's say this is x is equal to pi, this is pi. Clear? So x equal to 2 pi, x equal to 3 pi, let's say. Similarly here you draw x equal to minus pi. Okay, so this is x is equal to minus pi, x equal to minus 2 pi. Okay, so this is x is equal to minus 2 pi. Similarly x is equal to minus 3 pi. Okay, so we have drawn these values. Now try to understand something. This is pi, of course, this is 2 pi, this is 3 pi. Okay, and similarly this goes up, and similarly this is minus pi, of course, so this is minus pi, minus 2 pi, minus 3 pi, and of course you can keep generating. Now you can see sin 0 is 0. When you put x equal to 0, the value of this function is undoubtedly 0 here. Now at pi also this is 0, and when x lies between 0 to pi, this function is positive because you know sine is positive from 0 to pi. So from 0 to pi, it just takes the shape of sin x. Okay, and here it again falls and it goes up, and again here it goes up and falls like this. Similarly, this function will also be like, of course it is symmetric exactly. Okay, maybe the graph may not look exactly symmetric because of my drawing, but this graph is actually symmetric. You can see this will actually generate. How I know it is symmetric is because I've told you one point yesterday. If f of x comma y is equal to f of minus x comma y, then graph is symmetric about y-axis. I have told this point, correct? So graph is symmetric about y-axis. Clear? So if graph is symmetric about y-axis, now you take this function, you have y minus x into sin x is equal to 0. Correct? This is what you have, and because if y equal to x sin x, y minus x into sin x is equal to 0. If you replace x with minus x, let's see what happens here. Y minus, instead of x, I am putting minus x into sine of minus x is equal to 0. This is what you have, f of minus x comma y, of course, and this is f of x comma y, let's say. Now if you simplify this, y minus x into, you know, sine of minus x is actually minus sin x, correct? So this is minus sin x is what you have, is equal to 0, and you can observe this minus and this minus cancels, and you have f of minus x comma y is equal to y minus x into sin x is equal to 0, and this guy is again same as f of x comma y. Okay, so whenever this is f of x comma y, and if you replace x with minus x, if the function is not changing, then definitely the graph has to be symmetric about x, this y axis, and obviously this is what the symmetric curve you will generate. It is bounded by this. Normally you'll generate these curves, you might have seen. Okay, so then for y equal to mod x into sin x, these fellows will actually come on the top. Okay, mod x into sin x. Okay, so you are talking about mod x into sin x. So the graph will come only for the positive values of x then in that case. Sorry, y equal to mod x into sin x. Okay, so if you take mod x into sin x, then when x is positive, if x greater than 0, it's like x sin x, which means on the right hand side this part, and on the left hand side it will just flip. Okay, so when x is less than 0, you have minus x into sin x. So on the right hand side this graph remains same. On the left hand side these values, means here this will be a reflection about y, this x axis. That's all. Clear? Okay, on this side basically right hand side remains same, but on the left hand side this will be there will be a flipping reflection about the x axis because of this minus sign. Clear? Okay, did you all understand how we are drawing this graph actually? And many times you will see this graph. Okay, why I have taught this graph is not like I am very much interested in this, but we encounter this graph many times. You might have seen, for example, if you look at this positive, you might have learned something called the undamped vibrations. You know, if your disturbance in the system keeps increasing, then the amplitude of the noise keeps increasing. Yes, you might have seen this kind of stuff in your technical subjects, correct? Normally if you are dealing with undamped vibrations or undamped noise, in such case what happens, this amplitude of the noise keeps increasing or amplitude of the vibration keeps increasing for every phase, correct? This is what you have. Got it? Is this clear to all of you? Okay, and you can see, even if you plot this graph, of course with a lot of understanding we have plotted, but nowadays you have plotters. You just use maybe Desmos graphing calculator. Okay, so if I write y equal to x into sin x, let's see, that comes up. Let's see here, y equal to x sin x, x into sin x is what you get. Okay, x, okay, dot, maybe it hasn't taken, just a minute. Okay, fine, x sin x is what directly you can plot. So you can see this is x into sin x is what I have plotted. So this is something what I have created up to this, maybe up to 3 pi. So this is like 3 pi roughly, and minus 3 pi is somewhere here. So I have tried to draw the plot between this. So you see this graph exactly looks symmetric about this vertical axis, because if you change x with minus x, the functional value doesn't change. Okay, so because of that reason this graph is symmetric about y axis, and you can see ultimately if you plot these points, See, for example, you can see this is 0, then ultimately it is pi by 2, right? So pi by 2 comma pi by 2 will be this point. Okay, so this point is actually, it is bounded by this line. So let's say correct 7.97. See, because this slight errors come up in the sin x calculation, but in fact this is bounded by this y equal to x into sin x, of course. Okay, that's what. Clear to all of you? Yes or no? Did you understand how we can plot this x into sin x? Of course. Yeah. Now let's go for one more graph, sin x by x. Okay, so 7, 8. Y is equal to sin x by x, and in bracket x is not exactly equal to 0. Okay, so x is not very much is equal to 0. Now how to plot this? Let's see. Again, first let us develop the coordinate system, then we'll see what's the story. Fine, so let's see. Origin x y, of course. Okay, so y equal to sin x by x. Now again, let's do the same analysis. You know, -1 less than or equal to sin x less than or equal to 1, of course. Then this implies -1 by x less than or equal to sin x by x less than or equal to 1 by x, of course. Okay, and you know x is not equal to 0 in this. X is not equal to 0. So one thing is very clear, this sin x by x lies in between the curves y equal to 1 by x and y equal to -1 by x. And you know y equal to 1 by x. You know how y equal to 1 by x appears? Y equal to 1 by x is normally called rectangular hyperbola. Rectangular hyperbola. Rectangular hyperbola. And you guys know, normally all of you might have studied thermodynamics in your class 11, maybe. Okay, in your basically in your class 11 you might have studied thermodynamics. You all remember this equation, PV is equal to mRT. Have you all remembered this equation? Yes or no? If you take an ideal gas, and ultimately if the ideal gas is at some volume and some temperature, the pressure exerted by the ideal gas is given by that equation. Do you all remember that? Yes or no? Please type in the chat box. Correct. Now ideal gas equation. Okay, so if you take this equation, then ultimately if your temperature is constant, okay, you have something called isothermal process. Now in isothermal process, if you make this T is equal to constant, and if you put the gas in some container so that the mass cannot escape, and this depends on the type of the gas, so right hand side becomes constant. Okay, so PV is equal to constant, and P is inversely proportional to 1 by V. You might have studied this as Boyle's law, if you remember. Correct? You might have studied this as your Boyle's law, of course. Or maybe P equal to some constant divided by V. This is your Boyle's law. Find an ideal gas at constant temperature, P is inversely proportional to V, is what you might have studied. So why I'm talking about this simple stuff is, this equation, if you take instead of 1, if you take 2, 3, 4, whatever, I generally mean this is a constant. Y equal to constant by x gives a shape of rectangular hyperbola, and that's what we exactly need in this equations. So if you plot y equal to 1 by x, let's see how we'll get the curves. Okay, so y equal to 1 by x is something like this. Okay, and of course this is how your lines y equal to 1 by x looks like. As x increases, ultimately y keeps decreasing, and here also as x increases, y keeps decreasing. Okay, this graph, actually this is the graph of y equal to 1 by x. This graph tells you one very important point. Can anyone tell me, now you have enough idea on limits, limit x tends to 0 1 by x. Can anyone tell me what is the value of this by looking at this graph? Because you know, by this time you got the idea what is the definition of a limit. So if this is the graph of y equal to 1 by x, I didn't draw sin x by x, I'm just putting 1 by x. So if this is y equal to 1 by x, at x tends to 0, what is the value of limit x tends to 0 1 by x? Any idea that you have? Limit x tends to 0 1 by x. Anything that you know about it? Undefined, or basically it's not undefined, it's defined, it does not exist. Okay, undefined means we don't know actually. Okay, but here you see this does not exist actually. This is one very important statement again. Limit x tends to 0 1 by x does not exist. Okay, why it does not exist? Yeah, does not exist, exactly. Okay, why it does not exist? Because you can see, if you take right interval, limit x tends to 0 plus 1 by x. This value, if you see in the right interval, the value of 1 by x tends to plus infinity. Okay, so this is plus infinity, and limit x tends to 0 minus. You take the left limit 1 by x, then you can see whenever x is tending to 0 minus, of course, so within this value, the value of 1 by x is minus infinity. Clear? And these two guys are not equal, of course. Okay, negative and positive, different values. Yeah, 2. Okay, so that's why, because of this, the limit of x tends to 0, 1 by x does not exist. Many students, they write the answer as infinity, and even for making students write infinity, they'll give the first option as plus infinity. Okay, but this limit does not exist, because I've told you, if you plot the function and if you try to approach 0, okay, from any side, doesn't matter, your function value should tend to the same value. Okay, like if I start here and if I keep moving towards 0, it is plus infinity, and if I start at this point and if I start moving towards 0, it is minus infinity, and these two are not equal. That's why this limit does not exist. Clear to all of you? Yes or no? Everyone? Sachiti, Chauhan, Sagnika, Kshenan, all in one. All in one, nice name. Is this clear to all of you? Okay. Now, this function is very important function, sin x by x, of course. The reason is this function actually cannot be handled with the help of maximum and minimum concept. Okay. So anyway, you know the maximum value is somewhere here, but you don't know exactly where it is. So anyway, coming back to the story, you know, this function lies between 1 by x and minus 1 by x. These two graphs are for y equal to 1 by x, you know. Okay. So this is y is equal to 1 by x, and this is also ultimately y is equal to 1 by x. Now, what about y equal to minus 1 by x? Okay, so if you plot y equal to minus 1 by x, ultimately if x is negative, then y is also negative. So the values of y equal to minus 1 by x comes up like this. Okay, this is how you have y equal to minus 1 by x. These two graphs, they suggest the value of minus 1 by x and y is equal to minus 1 by x. Okay, y equal to minus 1 by x. Now let's see, exactly at x equal to 0, you cannot tell anything, because 0 by 0 and 0 by 0 is undefined form. Okay, so when you put exactly x equal to 0, you cannot say anything, but you can understand something here. As x goes long, okay, as x value increases, what happens here is this function on the numerator is always some finite number, correct? This function sin x on the numerator always lies between minus 1 and 1, but if x is kept on increasing, then what happens? Ultimately, the magnitude of the function keeps decreasing. That's what it tells you. Whatever you have to draw now, you have to draw in between these 4 lines, and as x increases, the amplitude of the function keeps decreasing. Okay, you can see here clearly on the left hand side, the amplitude of the function also keeps decreasing as the mathematical or the absolute value or the numerical value of x keeps increasing. And if you see the sin x by x, again the same pattern follows here. You can see if you plot this, the shape that you can generate is ultimately the sin x between these two. It dies down similarly. You can see this also dies down, and this value is pi, of course, and this is 2 pi, 3 pi, and so on, whatever. Similarly, this is minus pi, minus 2 pi, and so on. Okay, this is minus 3 pi, of course, and you can see here also the function is symmetric about x axis. Okay, sorry, it's symmetric about y axis. The reason is here, if you replace f of minus x comma y is same as f of x comma y here, because sin of minus x is minus sin x, and if you replace this x with minus x, this minus and minus gets cancelled. Again, you will have sin x by x. Okay, and this is how you'll get the graph. Now, if you observe one thing very exclusively, if you just zoom in, if I just zoom in, you can see this function is discontinuous at this point, correct? Because exactly at x equal to 0, I don't have the value for, basically this value. So that's why intentionally I'm not connecting these 2 points. In fact, at this point x equal to 0, I am leaving the space. Okay, I'm not connecting it. Clear to all of you? Did you understand why I'm not connecting the graph at this points? Because exactly at x equal to 0, the definition or basically that division is not possible. You cannot do that. Okay, that's how this function has a discontinuity, and you will see, but the maximum value is coming around x equal to 0. Okay, if you apply the classical concept of maximum and minima, your second derivative test will fail. Okay, because at the stationary point, you will, at the stationary point, of course, I will discuss this in detail maybe on Monday's class. So you will see why at 0 maximum value, because this x value is very small when x is tending to 0, and because of denominator approaching is 0, the function approaches maximum at very close to 0, of course. Clear? And even if you do the classical maximum minimum analysis, you will find out, of course, that analysis second derivative test fails, but using Taylor series expansion, if you try to calculate, you will have this function having maximum value around x is equal to 0. I'm not telling exactly, but somewhere around x is equal to 0, it has the maximum value, and you will find out the maximum value. Do anyone know what is this maximum value? Let's say, for example, here it is coming up to be maximum almost. Can anyone tell me what is this value? What is this value? But at 0 sign max na, sir? No. See, that's what I'm telling now. Whenever you have the sign value very small, but the denominator is much smaller, and this value keeps increasing, because I'll just tell you one thing. Just give me a minute. This value is 1 first of all, and from which you'll get the very important limit x tends to 0 sin x by x is equal to 1, of course. Okay, so limit x tends to 0 sin x by x is equal to 1. This very important limit comes up from this graph actually. Okay, so as this approaches, this functional value touches 1, and I'll tell you one important thing here again. This limit is very important when x is very small, because someone has asked me this question. Who? Prabhat. Look, when x is very small, sin x will be less than x, of course. Okay, so sin x will be less than x, and whenever you see this function, if you take this value, when you're going very close, both these values start going very close towards 0, but this sign decreases much faster, and totally the function achieves a maximum. I'll show you maybe here. You can see, you can just this is y equal to x into sin x, of course, and I'm erasing this for the time being. So sin x by x, you'll see, sorry, keyboard, just a minute, I'll plot it and show you maybe. Sin x divided by, is this divided by symbol slash, yeah, divided by x. So you can see this is sin x by x is what I'm plotting. It's in red color. So if I just zoom it, okay, so if I just zoom it, you can see, of course, I have done it very exaggeratedly to make you understand, but you can see this value keeps increasing, and as you go in this direction, like for example, this gap is more as compared to this gap, and this gap is more as compared to this, and this is more as compared to this. So this function actually dies down. Okay, inside 1 by x area, is it with trial and error? No, I have done now. See, because of this analysis, you know, this sin x by x always lies between this y equal to minus 1 by x and y equal to 1 by x. So that's why, you know, graph lies only within this region. Clear to all of you? So this is how you get the graph of sin x by x, and this is the axis, and clearly at this point, you can see at this point they'll just give you exactly at 0. You can see the graph I'm showing exactly at 0. The y value is undefined because division with 0. But if you slightly move, okay, 0.01, 0.02, if you go to that range, y value is 1, which you can see here. Okay, I hope I can maybe expand and show you. Exactly at 0, you cannot find the value of function. You can see there. Okay, so 0, it's undefined. Clear? I'm just moving my cursor slightly. Fine. See here, exactly at x equal to 0, function value is undefined. But if you slightly move 0.01, the value is 1. Okay, so that's why, you know, this comes up to maximum value 1, which gives you one very important limit of limit x tends to 0 sin x by x is equal to 1 actually. Okay, and this maximum value is calculated from graphical visualization and Taylor series, and that's why you'll get x is equal to 1. I'll talk about Taylor series maybe in tomorrow's class, because today time won't be sufficient. So we'll go for Taylor series, then we'll see why sin x by x gives 1 when x is very close to 0. Okay, we have a nice explanations here. Clear? Are you all understanding? Yes or no? Please type in the chat box. Is each and everything clear or not? Okay, this is the story of sin x by x, and this has some good influence with this isothermal process and whatever. Now let's go to one more thing. Ninth graph, y equal to sin 1 by x, and of course x is not equal to 0 again, because you know at exactly 0, division with 0 is not defined. Sin 1 by x. So let's see how we'll get the graph of sin 1 by x. So ultimately the graph value keeps sine. Okay, so sine is always in between -1 and 1. You know, this is y equal to 1, maybe this is y equal to 1, and this is y is equal to -1. Let's say this is y is equal to -1. Clear? Because whatever you keep here, this sign always gives you. So the graph lies somewhere in between. So this is y is equal to 1, of course, and this is y is equal to -1. So you know, ultimately after some limit, the function die down to 0. Here also the function, because if x value is very large, then once x value starts beyond certain limit, then ultimately this 1 by x will become very small and sine 0 will come very small. And if you check, for example, if you check this value, when this value is 1, okay, so sine 1 by x is equal to 1, of course. So if you check this point, 1 by x has to be pi by 2, so x has to be 2 by pi. Okay, so similarly on the other side, sine 1 by x is equal to -1. This implies x is equal to -2 by pi, of course. Now tell me one thing, at this point of 2 by pi, if you keep increasing your x beyond 2 by pi, okay, or if you keep your x beyond 2 by pi, then ultimately this 1 by x will be less than pi by 2. Yes or no? Correct? Did you understand this point? If your x is 2 by pi and then 1 by x is pi by 2, if you keep increasing value of x beyond 2 by pi, then ultimately this value will be always less than pi by 2 and sine will be always positive after this value of 2 by pi. Correct? After the value of 2 by pi, sine 1 by x will always give you positive function, because x can never go beyond pi by 2. Okay, it lies, and x is positive, of course. Okay, because this x is always positive, we are going on the real side of the x axis, so this value is always positive. Clear? Yes or no? Similarly, if you go beyond -2 by pi, that function will be always dying down to 0 again. Okay, now let's see. If you first, I'll show you the plot. Okay, first let me draw the plot actually. So if I show you the plot comes up like, it goes to 0 after this. Similarly, this also goes to 0 after this. Okay, and within this region, you'll see there is a sine wave which will have decreasing, means these lines keep coming close. Okay, this function keeps coming very close. Exactly, this function keeps coming very close, of course, and again exactly at x equal to 0 is not defined. Then after, it again slowly keeps increasing its magnitude, increasing its length, and it connects like this. So within the region which is very close, all the graphs will actually merge so much. Okay, the reason for this is, when x is equal to, see, if you want to make this guy as 0, 1 by x is equal to 0, for example, you know, if sine 1 by x is equal to 0, means if 1 by x is equal to integral times of pi, x is equal to 1 by n pi is what we have. So which means x is equal to 1 by pi, x is equal to 1 by 2 pi, x is equal to 1 by 3 pi at all these points, and x is equal to, you know, at x is equal to 1 by 4 pi, 5 pi, and so on. Whatever you have, large number of pi's, ultimately this all points will be zeros. Okay, and you will have many points like 1 by pi is somewhere here. Okay, because I told you this is 2 by pi, which you have understood from that. Now let's say this is 1 by pi, 3 by pi, 4 by pi, 5 by pi. So within this length, the values of this x values where sine becomes 0 is very small. Okay, so what does it mean in real life when the amplitude is getting close? Means because you can have functions where the wavelength is increasing. Okay, so if wavelength is increasing with time, let's say if I plot time and some wave I'm plotting, if wavelength is increasing with time, then ultimately this basically you have this in many cases, like in Fourier series when you're dealing signals and systems. Okay, then what you have, with increase in time, the spacing between the nodes increases. Okay, so wavelength actually increases with time. Clear? Now let's see if I plot this, maybe sine 1 by x, I'll plot and show you sine 1 by x. So if you see, yeah, maybe this is the graph, you can see this is what exactly I tried to replicate. So this is my pi by 2 by pi, of course, and this 2 by pi, after this the function keeps increasing but the value keeps decreasing because x value keeps increasing. So this approaches 0 and it die down to 0, x y, this is minus x, of course. Okay, and this goes to -0, and in between the wavelength keeps decreasing. The reason, when you go from 1 by pi to 2 by pi, 1 by pi is exactly at half of this complete location. If you take 0 and 2 by pi, 1 by pi is exactly in between, but 1 by 2 pi will be exactly again half of that. 1 by 3 pi will be again half of that space. So the spacing between the nodes keeps decreasing, okay, because as this number increases. And if you see, for example, this is how the graph you actually get. Like, for example, you know, this value, if you check, it would be 2 by pi, of course, okay. So 2 by pi, let's calculate the value. 2 by pi, if you check, 0.6366, which if you round off 0.637, that's what they have given you here. 0.637, is what you have. Exactly at this point, the function, anything after this keeps decreasing, and this will die down to 0, of course. You can see as x goes to infinity, this function is having 1, of course. Any of these values are 1, okay. 0.987, 0.99, if you go, you'll get 1. But this graph keeps getting down 0. After this point, it never is negative, okay, because pi by 2 value, x will be less than pi by 2, of course. Clear? Okay, so that's how we have this graph. Did you understand? See, the basic idea why these graphs beyond this point, why they come very close is, you see, if this is 0, okay, and this is 2 by pi, or 2 by pi, of course, then you know 1 by pi will be exactly at the midpoint. Now 1 by 2 pi is exactly at this point. 1 by 4 pi or 1 by 3 pi, 1 by 4 pi will be in between this. So you can see at all these points the function is 0, which means here if the function is reaching something like this, or maybe say something like this, it will touch 0 here and it will come back here. So this gap will be large as compared to this gap. So that's why as you come close to 0, the loop gets compressed. Clear? This is one important graph actually in signals and systems, especially when you are working with Fourier spaces. If you deal, this is very important. Okay, clear to all of you? You might have seen the control systems. The noise in the initial stage at time, very less time, it will fluctuate a lot, but slowly dies down after some time. Okay, clear to all of you? This is the graph of sine 1 by x, of course. And why I'm teaching all these graphs? They are all asked in many interviews. Okay, that's why I've taught. I myself was asked x into sin x when I applied for PhD at IITM some time back. Then sine 1 by x was in one of the interviews. I remember it's BRC because I have written maths as my favorite subject. Okay, so like this at many places they have played with me using graphs. And of course, since when and in all these places I have able to clear the interviews, because when I taught at JEE Advanced, okay, there's a book which I love so much, Play with Graphs. You know, there's a nice book actually which you can get. Maybe I'll show you the copy. I think you cannot get a copy, but you can buy it actually. At least I'll show you the homepage. Play with Graphs is the name of the book, of course. So Amita Agarwal sir has written this. You just look at the images. You know, this edition is very much famous edition. You can see the review. Around 235 rupees is the cost of this book. But Play with Graphs is like I even have a copy now. Now in the sense not exactly in this room, but you know, I have it in my home. I love the book so much. Okay. So if you know graph, you can tell a lot of things. If you have a sharp edge, okay, then ultimately at that point derivative is derivative does not exist actually. So you can talk about all this point. Clear? Okay. Is this clear to all of you? Then we'll talk about 2 more functions and then we will go to some standard derivatives. Okay. Then let's see. Are you all enjoying or not? Is it too boring or understandable? Are you all enjoying the things? No? Yes? Nothing? Yeah? Understandable? Okay, some hearts are floating, so I think understandable. Good. We'll see 1, 2 more graphs before we go. 10. You can see maybe is, 10th graph is like greatest integer function. Or it's also called as step function. Of course, if I keep talking about that functions, you have a number of functions, but I'm just giving which are important graphically a bit for gate examination level. Okay. So greatest integer function. And you know what is a greatest integer function? Of course, this function is defined in such a way that f of x is equal to, this is denoted with this symbol x in a square bracket, which is equal to x for all, okay, is equal to x for all x less than or equal to, or x is equal to n, f of x is equal to n for all n less than or equal to x less than n plus 1. Please make a note, there is no equality sign here. Okay, here there is an equality sign in the left neighborhood, but in the right side there is no equality sign, means and where n belongs to integer. N belongs to integer. Okay, so n is an integer, so you can start with any, means if you have any two integers, and of course it's the greatest integer function, then n less than or equal to x less than n plus 1, it is the n is what you have here. Okay, now if you plot this, it's also called step function. We'll see why in a short time. If you try to plot this function like this somewhere, okay, so let us plot this. This is origin, this is x, and this is y, of course, and obviously minus x and minus y. Now, first of all, before drawing the graph, we want to again do some certain analysis. Look, if I ask you integer part of 2.317, can you tell me what is the answer? What is this value? From this definition, you know, for any value of x lying between two integers, the least integer is actually the value of that function. Okay, so if I write 2.317, what is the integer part of that function? This is also called integer part function. Integer part function. Okay, so this is integer part function. So what is the value of this? You know, it's 2, correct? Because ultimately this 2.317 lies between 2 and 3. So if you put n equal to 2, then ultimately 2 less than or equal to 2.317 less than 3, of course. Okay, so this value has to be n, so this is 2. Can anyone tell me what is minus 1.345? Let's say, what is this value? What is that value? Can anyone tell me? Can anyone tell me what is the integer part value of minus 1.345 actually? Quick, a bit faster. Plus 1. No, this is not modulus function. Okay, minus 1, minus 2. Kundan has typed minus 2. Yeah, 2. Of course, this value is minus 2. The reason is, you know, in negative numbers, as you go towards left, the number decreases. So this value lies between minus 2 is less than minus 1.345 is less than minus 1. So clearly this value is on the left side. So this is minus 2 up. Okay, so that's how the value is minus 2. Clear? Now, if you want to plot this function, let's see how we can plot. Let's split this domain into some parts. Let's say this is x is equal to 1, of course. Okay, then you have maybe x is equal to 2. Clear? I'm plotting this. X is equal to 2, x is equal to 3. Fine. Then x is equal to 4. I'm just stopping here because I just want to confuse things again. So this is x is equal to minus 1, equal to minus 1, x equal to minus 2, x equal to minus 3, then you know x equal to minus 4, of course. Clear? So this is x is equal to minus 4. Now let's understand. Similarly, if you draw the lines y equal to 1, let's draw this. Okay, let me again draw the dotted line. So y equal to 1 is something like this. Basically, I just want to generate a square grid so that I can explain you better. If you put y equal to 2, then if you put y equal to 3, of course. Okay. Similarly here down the line, y equal to minus 1, y equal to minus 2, then y equal to minus 3. Okay, so let's say this is y equal to minus 3. Now if you draw these elements, this is x equal to 1, x equal to 2, 3, 4. Similarly, minus 1, minus 2, minus 3, minus 4. Okay, so this is what we have. Similarly, if you look at the y values, this is y is equal to 1, y equal to 2, y equal to 3. Similarly here 1, 2 and 3, of course. Now try to understand something. If you take any value between 0 and 1, okay, if you put n equal to 0, 0 less than or equal to x less than 1 means for any value between 0 and 1, this integer part function is 0, correct? Means you take any x value between 0 and 1, the value of y is 0 actually. Means if you plot this, this graph will come something like this, okay? This graph will be coming something like this. And you can observe one thing here. If you zoom in, I am not touching this graph to 1, okay? I am not touching this graph to x equal to 1. Why I am not touching? Because there is no equality sign here, okay? So because of no equality sign here, I should not touch my graph to 1, of course, okay? So similarly, you can see for any value between 1 to 2, the value of y is 1. So this graph comes like this. Similarly here, you can see this graph comes up like this. Similarly here, it comes up like this, okay? And similarly here, you know, this starts here and it does not touch 0. Similarly here, the graph part comes like this, and here it comes up something like this. So all these green shaded lines are basically the steps, okay? So you can see if you check all the green dotted lines, ultimately this graph looks like a steps. So that's why it is called step function. And especially when you have the discrete signals, this step function is used many times, okay? So if you just try to plot this, let's see if we can plot this, okay? Yeah, so sin 1 by x, of course, I think you had enough fun in looking at this graph. So if you keep zooming in, you'll have so many steps which are very closely packed, okay? Then integer part x, let's see if we can plot this. Integer part x, okay? So okay, I think this is taking only y equal to x, maybe. So greatest integer function. So plotting, I'll just maybe show you greatest integer function. So that integer function plotter, okay? So integer function plotter, okay? So if you plot this greatest integer function in Desmos, you can see here, okay? So what we should type, they have generated some values, of course, x equal to minus 5, 4. So floor x is the function, okay? Floor x is the function. If you plot this, you can clearly see they have done this steps again here, but on the right hand side they have denoted a empty dot, because exactly at this point, means at every case exactly at the ending point, this function do not have the value here as 1. In fact, it is 2 here, okay? So that's why there's a sudden jump from 1 to 2 at this point, and clearly this graph is discontinuous at every integer, okay? So this is how you have the greatest integer function, which is basically represented here. Clear to all of you? Okay, is this clear to each and every one of you? Now we'll write one important point. Limit x tends to a, integer part x does not exist if a is an integer. If a is an integer. This point is again very, very valid and important point, okay? So you can see this function does not, this limit will actually does not exist, of course, okay? The reason why it does not exist if a is an integer is, let's say if a equal to 2, for example, okay? Then if a is equal to 2 here, then within the left neighborhood, means if you are interested in this story at exactly at x equal to 2, in the left neighborhood, means somewhere here, if you work in the left neighborhood, this value is 1, okay? So clearly this is the line y equal to 1, so this value is 1. But if you slightly go to the right neighborhood, then ultimately at this point the value of the function is 2. So exactly at that point, if there is an integer, exactly at integers, the left hand limits and right hand limits are not equal, and the limit does not exist, okay? And in fact the function is also discontinuous. You can see there's a breaking at every integer for this function, okay? If a is not an integer, okay, so let's say if a is 1.5, it's not an integer, at a equal to 1.5, what happens? See, if you take it 1.5, in the left neighborhood the value is 1, and in the right neighborhood also the value is 1. So there won't be an issue there if a is not an integer, okay? But if a is an integer, ultimately limit does not exist, because both left and rights will not match. Clear to all of you? This limit is also one of the important limit which has turned up in gate examination a few times, okay? So this limit will not exist if a is a integer. Clear? Apart from integer, you take square root of 2 irrational numbers, square root of 3, square root of 4, you take any irrational numbers, real numbers, limit exists always, okay? Clear to all of you? So please type in the chat box. Yes? Then let's try out something else. So okay, so I hope it's clear to all of you. Then we'll talk about one important last function before we move. So 11, you can see Signum function. Signum function, or sometimes it's also called as SGN, normally called for Signum, SGN of X. Okay, again, you might have studied something about Dirac delta, which you'll see in technical subjects. So in there, you'll see the function is defined in such a way, SGN of X, especially when we are dealing probabilistic, and especially in this basically discrete Boolean algebra, we'll come across this. So this value is 1 if x greater than 0. This is exactly 0 for x equal to 0, and this is -1 if x is less than 0. Okay, so normally the Dirac delta function is also defined based on this. So let's see, if you plot this, then ultimately it's an easy thing to plot compared to all other functions. So when x is positive, this is origin, then this is x, this is y of course, and this is -x. So clearly when x is positive, ultimately the graph comes up like this. Okay, intentionally I'm not touching this graph to y axis. Yeah, intentionally I'm not touching this, because you can see if I zoom in, you can see this two did not touch. Okay, so that's why intentionally I'm not touching this, because exactly at x equal to 0 the value is 0, which means this is 0 of course at this point, and if you go to negative, this is -1. Okay, so this is y is equal to -1 of course. So y is equal to -1. This is how the graph of Signum function is there. If you have confusion, please ask me. Okay, no issue. Clear? If you have any point to ask, please ask me. Just a minute. Yeah. So please type. If you have any confusion, please ask me right away. What about pi? Will it exist as it's non-terminating? Pi is just a constant, right? Okay, pi is actually just a constant. Clear? Okay, so pi is just a constant. Pi is not a function. Clear? Pi is a constant value. Fine. Okay, yeah, it exists, right? Pi is defined, well defined, it's a constant. Okay, so 3.14. Clear? Actually, if you understand one thing, pi has a very beautiful consequence. Okay, so the basic value of pi, if you see the connection, it comes up from collisions. Okay, so initially if you check the collisions, okay, then the idea of collisions is behind the generation of value of pi. You know this theory? It's not exactly 22/7 of course, but we have slightly modified it. In fact, the constant value 3.1417 and so on, that is approximately equal to pi of course, but in general this 3.1417, whatever the numbers you have generated, that value came up from, again, mechanics point of view, collisions. Okay, so collisions is what that gave us the value. You know this? Number of collisions when two blocks collide, depending on the masses, the number of digits of accuracy of pi comes up. Have you seen this anytime? Yes? No? Never. In fact, there's a good research paper actually on this. You can see. Maybe I'll just give you some idea. Collision of blocks to pi. Maybe I can. Value of pi. Okay, so you can see this calculating pi with yes, Galpin billiards of course. So you can see, you click this, there's a research paper which gives you the basic idea of pi. I think this is the paper, but that's opening up. It's a very beautiful paper which you can see many times. Okay, yeah, the dynamics of digits, calculating pi with billiards of course. So if you see the number of collisions that actually happens with the wall, yeah, of course. Okay, so if you see, this is mass m and this mass v, if you collide, then this value finally, if you, after doing a bit of understanding of mathematically fitting the values and all, it putting in some maths here and doing stuff, then it will actually give you the value of pi in general. Okay, this is the main function which generates the value of pi by arc b power arc tan is basically tan inverse of b power minus n. So these things will finally yield the value of pi in general. Okay, the number of digits of accuracy comes from changing this m actually. Okay, a bit of quantum mechanics again comes into picture. So it's a nice paper actually. Okay, I didn't go to this exact same paper, but I have gone to some another research paper actually, which can give you some idea. Production of PP collisions, no. Statistical theory, no. There's one book actually, okay, which providing blocks by simulation. I think here you have this. Okay, maybe yeah, it's not working, but anyway, GitHub you have this, so you can just try it up. It's a nice stuff actually to read. And the last, okay, so this is basically the Signum function. Okay, so these are some graphs which are useful to you, which I have given you, of course. Simple graphs, then mod x, then x into sin x, then x sin x by x, then sin 1 by x, of course, then greatest integer function Signum x, and you can keep talking about a lot of graphs, but again you have to put a limit, of course, so we are stopping here. Now coming to some standard derivatives which help you. We have seen what is a derivative. Basically derivative gives you slope of the tangent at that point to the function. Okay, and whatever the direction you oppose that point, ultimately the slope of the tangent has to be same. Okay, now let's see some standard derivatives which I just give the formulas. Okay, so d by dx of sin x. Okay, you know what is this value? Okay, easy stuff, I'll just write it. D by dx of cos x, so then tan x, all this some basic things I'm writing quickly. Cot x, secant x, all this is pretty much basic stuff which you all might have seen. Okay, so I'm not putting much time here again. So d by dx of x power n, of course, this is also one thing. Then coming to the inverse trigonometric, d by dx of sin inverse x, all these are very much important. Okay, we keep day to day with these functions, we deal with these functions almost every day. Cos inverse x, I'm just giving the list so that it would be helpful to you, and many of you might have known this list of course previously. Cot inverse x, okay, then secant inverse, cosecant inverse x. Okay, so you have these things. Then similarly you know, we can give 14. So trigonometry got finished. Then after you know, polynomial I have given, algebraic functions I given, then inverse functions I given, logarithmic. So d by dx of log x to the base a, 15. D by dx of log x to the base e, general natural logarithm. Then this got finished. So exponential functions, a power x, so 17. D by dx of e power x, d by dx of some general functions which we deal day to day, mod x, 19. D by dx of maybe some x power x. Okay, this is also a bit important. Yeah, I think these functions could be more than enough. Okay, inverse functions I given, logarithmic I have given, exponential, then algebraic, yeah, 2, and trigonometric, yeah, we have given everything. Okay, and maybe some hyperbolic functions also you may need. Sometimes in some technical subjects they're asking questions like fluid mechanics and all times they came. Derivative of sine hyperbolic and derivative of cos hyperbolic functions, and you can do the rest of the things based on your calculations. So chalo, now I'll keep filling this list. Okay, you all know derivative of sin x is cos x, then cos x minus sin x. Again, any of these things can be the first principle of differentiation. Then derivative of tan x, secant square x, derivative of cot x minus cosecant square x, then secant x, you know, secant x into tan x is what you got, then cosecant x. minus cosecant x cot x is what you get, minus cosecant x cot x. Then x power n, ultimately n into x power n minus 1. Okay, so that's a common thing that you have. Then sin inverse x, if you differentiate this, you'll get 1 minus root of 1 minus x square. Then cos inverse x minus 1 by root of 1 minus x square. In both these cases, mod x less than 1, here also mod x less than 1, otherwise we'll enter the complex regime again. Then derivative of tan inverse x 1 by 1 plus x square minus 1 by 1 plus x square, because in trigonometries we have sin inverse x plus cos inverse x. Whenever x lies between minus 1 to 1, this value is pi by 2. Okay, so if you differentiate both sides, derivative of sin inverse x plus derivative of cos inverse x equal to 0. So derivative of cos inverse is negative of derivative of sin inverse, so that's why this minus comes up. Okay, so again, all this is a bit of basic stuff. Which then secant inverse x 1 by mod x times root of x square minus 1, and here mod x greater than 1. Okay, because this should not enter the complex regime again. Minus 1 by mod x into root of x square minus 1. This is mod x greater than 1 again here. Okay, so these are the things. Clear? And you might know all these formulas, basically trigonometry and exponential, all these things you have seen. Now, can anyone tell me what is this derivative of log x to the base a? And in bracket, a not equal to 1, of course, because log is not defined for a equal to 1 exactly. So can anyone tell me what is that value? If it's an offline class, I would have played with you when filling this table. Okay, so come on, quick. Do anyone of you know what is the value of derivative of log x to the base a? d by dx of log x to the base a. d by dx of log x to the base a. A is not 1, of course, some general constant, and of course positive. 1 divided by x log e a, means log a to the base e, that's why you should call, yeah, correct. This is 1 by x into log a to the base e, of course. Okay, so this is what you get, and derivative of log x is 1 by x. Okay, you know this, and of course x positive in this case for logarithms, for the defining of log. And here if you put x a equal to e in this, log e to the base e, this term becomes 1 and it becomes 1 by x after. Okay, then a power x is basically a power x into log a to the base e, and this is e power x, obviously. Then derivative of mod x, can anyone tell me derivative of mod x? And of course x is not equal to 0 clearly, because at x equal to 0 it is not differentiable, so you cannot tell the derivative. But if it is not at x equal to 0, then at general, if you want to define the derivative of mod x, can anyone talk about the value of derivative of mod x? Quick, a bit faster, only last 35-40 minutes left, so please type in the chat box. Quick, a bit faster. What is the value of derivative of mod x at x not equal to 0, of course? No idea. No idea. If it's an offline class, I would have given you a chocolate if you have answered this. What's the derivative of mod x when x is not equal to 0? No idea. Mod x by x. Okay, so ultimately if x is positive, the mod x by x value is 1. If x is negative, the value is minus 1. That's it. Okay, to all right side of 0, ultimately the graph is y equal to x, so slope is 1. To all left, y equal to minus x, so ultimately slope is minus 1. That's what exactly given by this expression. Okay, so mod x by x is equal to 1 if x is positive. If x is negative, this is minus 1. Okay, then clearly x power x. Okay, fine. Anyone know about x power x? X power x. Does anyone know about it? What is the derivative of x power x? Because that questions came. Okay, they'll ask you the minimum value of x power x is dash. Previous gate question. Then ultimately you want to equate the first derivative to 0. All this stuff you have to do. Ultimately maximum value is infinity. As you keep increasing x value keeps increasing. But this function has got a minimum value. Okay. Any idea? What is the minimum? What is the derivative? So obviously you have to calculate minimum. Then you need first derivative to 0. But to equate first derivative to 0, you should know what is the first derivative. So what's the derivative? X power x into log e power ex. See, that should be it as log ex to the base e. Okay, yeah, of course. This can be written as x power x times log ex to the base e, or this can, in other words, be written as 1 plus log x to the base e. This is what we have. Okay, so this is the derivative in general. Okay, and sin hx, you know, sin hyperbolic is basically e power x minus e power minus x by 2. So this is cos hx, this is sin hx. There is no minus sign. Clear? So cos hx and sin hx are the values. Okay, and you know, of course, these 20 are generally the most frequently used things in our courses. And you know, product rule, of course. So product rule, or sometimes people, since they take this product of the functions as u and v, so they generally write this. So you can see this value is given as, the product rule in differentiation is given as d by dx of product of n functions. Okay, so we have product of n functions phi equal to 1 to n f of fi of x. If you have this, for example, okay, then if you have this function in general, this value is given as summation I equal to 1 to n. Okay, so you have summation of this functions f1 of x and into f2 of x into and so on. In general, I would like to write this as summation I equal to 1 product of I equal to 1 I not equal to j, where j equal to 1 to n, of course, this into of f of x fj of x into fi dash of x. This is how this product rule is defined. Okay, so because you know, I not equal to j, then j is running from 1 to n, of course. So if I and j are matching, then you'll skip that function in this part and you'll actually write the derivative at the outer state. Okay, this is the in the general n. If you have a product of n functions, of course, pi denotes multiplication and sigma denotes summation. And of course, in simple terminology, if you have only two functions, how this expression breaks up, let's see. If you have two functions, d by dx of f of x into g of x, you have two functions. Okay, now let's say you're starting from I equal to 1. Then when you put I equal to 1, then this j cannot be equal to 1 because for I not equal to j. So you have the second function, which is g of x into derivative of the first function as for this. So f dash of x plus, then again the same thing for I equal to 2. So you have f of x into then g dash of x. That's what this expression gives you. Really. Okay, so this product of two functions is first function into derivative of second plus second function into derivative of third. So if you have three functions, okay, so d by dx of q v w, if you have q v w, then this tells you something like uv into w dash plus u v dash w plus u dash v w. This is what you get. Okay, so first two into derivative of third plus first and last into derivative of second plus first derivative of first into last. Okay, this is how you have the derivative of product of three functions. In general, if you have product of n functions, this is what you will write. Okay, clear to all of you? This can expand. That's it. Okay, if you have four functions, then you get u v w z dash, then u v w dash z, like that. You'll have terms again. Okay, that's what. Fine. Is this clear to all of you? If you have product of two functions, then this is how you write product of three functions. Similarly, if you have product of n functions, this is the generalization. Okay, is this clear? Basically, this multiplication tells you if I is equal to j, then you have to skip that function in the product part and you have to write it in the derivative part. That's it. Okay, that's what we are doing. If you are deriving, then first two you are writing, then the third function you are skipping in the multiplication. Here you are not writing uvw because you need the derivative of third, so you are skipping w in this multiplication and writing the derivative of w separately. Okay, that's what it tells you. Okay, then so these are some standard derivatives which would help you at points. Okay, then let's go to some limits. Okay, so limits, in last class we have seen a lot of limits. Okay, then but there is some important thing. Okay, just from the definition of limit, we were not able to calculate the definition of many mathematical functions. Okay, so let's see what we can do. So the first thing we'll do is, now you have the knowledge of derivative, you can calculate what's the derivative. We can do something called L'Hospital rule, which is a bit important. Not a bit, many times, majority of the times we use this. Okay, L'Hospital rule. So it basically is defined for the ratio of functions. If you have two functions, okay, if you have a ratio of two functions, if limit x tends to a, f of x by g of x is giving you the form 0 by 0 or infinity by infinity, then ultimately you cannot define these values. Okay, then how this function or how this limit has to be calculated? Okay, it basically comes from the mean value theorem again. Okay, so you'll see, then limit x tends to a, f of x by g of x is equal to limit x tends to a, f, or in general this rule is given as f nth derivative, g nth derivative is given by f of n plus 1th derivative of x divided by g of n plus 1th derivative of x. Okay, so you can see here this f of n plus 1 of x, this gives you n plus 1th derivative of f of x, Loop will go on until this tie of 0 by 0 or infinity by infinity gets resolved. Okay, so let's say when you did this for the first time, okay, so let's say for example you're doing it for the first time, you take n equal to 0. Okay, when you take n equal to 0, 0th derivative of a function is nothing but the function itself, correct? Yes or no? 0th derivative of a function is nothing but the function itself. We are not changing anything. Okay, so the function remains as the function. Now first derivative, second derivative. So when you put n equal to 0, then if this is coming out to be 0 by 0 or infinity by infinity, okay, then 0 by 0 is giving infinity by infinity or 0 by 0, then this expression can be written as, when you put n equal to 1 here, first derivative of f of x, first derivative of g of x. Okay, if this is not 0 by 0 or infinity by infinity, then the answer is done. If this is also giving 0 by 0, again you come back, put n equal to 1. So if this first derivative ratio is giving 0 by 0 or infinity by infinity, you can go to second ratios. Okay, if this is not giving 0 by 0 or infinity by infinity, you'll stop this and you will basically declare the value, like how it is a while loop. Okay, is this clear? If you can understand, I hope it's clear. Okay, this loop keeps on repeating if you are not, if you are getting 0 by 0 or infinity by infinity. Actually, if there comes a point where your ratio is not giving any more 0 by 0 or infinity by infinity, you will cut this loop and declare the value. Okay, like example, let's see, we'll work out an example which example, let's say limit x tends to 0, 1 minus cos ax, of course I have given you as homework, I am solving this here, by x square, and a is some value. Okay, then if you put x is equal to 0 here, okay, if you put x equal to 0, let's see what happens. If you put x tends to 0 in this, 1 minus a into 0 is 0, so cos 0, 1 divided by 0 square, this is 0 by 0 form. Okay, so clearly this limit is giving 0 by 0 form, so ultimately you will fall into this loop. Therefore it's giving 0 by 0, limit x tends to 0, 1 minus cos x cos ax by x square can be written as limit x tends to 0. Look, here people will make one mistake, they'll apply u by v rule. Okay, but here I did not apply u by v rule, I am differentiating the functions independently. Okay, so this can be written as derivative of 1 minus cos ax, derivative of 1 minus cos ax, derivative of 1 0 minus derivative of cos ax minus sin ax into the inner derivative is a, because this ax is also one more function inside composite function, so differentiation of ax is a. This is what you get, divided by this value of differentiation of x square is 2x. So this has given me limit x tends to 0, this minus into minus gives plus, a into sin ax divided by 2x. This is what you got. Okay, I'm doing it step by step so that you can understand. So this is 2 by x. Now a and 2 are constants, there is nothing limit that can apply on a and 2, so we can pull this as a by 2 limit x tends to 0 sin ax divided by x. This is what you got. Okay, and clearly if you see in this case also you are getting a 0 by 0 form. Okay, means by starting from the functions, if you use the first derivative and if you try to calculate the limit, it's again giving you 0 by 0 form. Okay, so since it's giving again 0 by 0, you can again fall into this loop. So therefore this limit value is a by 2 into limit x tends to 0 sin ax by 2x. This is giving 0 by 0, so you can write this as a by 2, just a constant, into limit x tends to 0. Now if you differentiate this again, because you can fall into this loop, cos ax, derivative of sin ax is cos ax into the inner derivative of ax is a, divided by differentiation of 2x with respect to x is 2, of course. Okay, now if you put x equal to 0 in this, we have a square by 4. Okay, that's what you got, because 2, okay, I think 2 we have already taken, no, so there is only x here, sorry, there is only x, there is no 2 here, then this is 1, derivative of x is 1, then have a square by 2, and this is not equal to 0 by 0 or infinity by infinity. Clear? So the loop has ended. So ultimately, after running this loop for twice, undeterminate form is same as saying it does not exist. No, does not exist means you're 100% sure the value is not there. Okay, so it does not exist. But undeterminate means you cannot say whether it exists or it does not exist. Clear? Clear to all of you? Does not exist is something different from undefined. Okay, undefined means you cannot tell anything. Does not exist means you can tell there is no finite value that exists. You're 100% sure that it does not exist. Clear? So anyway, this value has ended up to this point a square by 2 here. Okay, so that's how you can keep repeating this loop until the tie of 0 by 0 or infinity by infinity ends. Okay, so this you will continue until 0 by 0 or infinity by infinity ends. This is the clear to all of you. Okay, okay, is this clear to each and everyone? Every one of you. So this value is basically a square by 2. That's what you have. Okay, so therefore limit x tends to 0, 1 minus cos ax by x square this is the limit. Okay, so this is a square by 2 in general. Okay, so basically this loop keeps repeating until this 0 by 0 or infinity by infinity ends at this point. So this homework question, if you go back just into this homework question which we thought of solving in the later stage, so now you can solve this easily. Limit x tends to 0, 1 minus cos x by x square clearly. Okay, so you know, since limit, of course you need not remember this formula, you can just work out. Okay, let me work out, you know, this is a square by 2, but if you generally work it out, limit x tends to 0, sin x by 2x, and this value is limit x tends to 0, cos x by 2 is 1 by 2. Okay, so that's what you can see. Basically you can keep differentiating until you don't get 0 by 0 or infinity by infinity form, and if you stop it here, stop it at that point, it is 1 by 2. Clear? This is 0.5. Okay, 0.5 is what you get. Clear? So let's see, and you know, note, you can maybe write here the same thing what I have taught you there. Limit x tends to 0, 1 minus cos ax by x square is equal to a square by 2. Since you know a equal to 1, the answer would be 1 by 2, which is matching. If you put a equal to 1 on both sides of this equation, then 1 minus cos x by x square limit x tends to 0 is equal to 1 by 2, which we got even from the. Now let's go back to some of the problems that we can work out using this L'Hospital rule, of course. Okay, so before this I would like to give some standard limits again, so which would be helpful to you. Some standard limits Okay, we'll give it later maybe. Okay, so let's teach some other difficult things. If limit extends to a, f of x power g of x is coming of the form 1 power infinity. Okay, so 1 power infinity, then this is also an undeterminate form. Okay, so this is also an undeterminate form. 1 power infinity, see, infinity is first of all not a number. Okay, so infinity is actually a symbol to denote a very large number, but exactly you don't know what is the number. Okay, so when I tell you 1 square, you can tell answer is 1, because you know you have to multiply 1 twice. Okay, but in first of all, this when I write 1 power infinity, you may have this doubt, 1 into 1 into 1 into 1 and so on, how many times you do it doesn't matter, the answer gives me 1. But first of all, to perform this multiplication, to close the operation, I should define what is the value, exact value on the power, and infinity is just a representation, it's a symbol to denote a very large number, that's it. Okay, so that's why this 1 power infinity is not a determinate form. Clear? This value is not 1, so please don't assume this is 1. Okay, then you know we can calculate this limit extends to a, f of x power g of x is equal to e to the power limit x tends to a, limit x tends to a, g of x into f of x minus 1. This is what you have as one of the standard operations. So this value power on this limit you can actually show by taking this function as y equal to f of x power g of x, and then by applying L'Hospital rule, all these things. But of course right now I'm just giving the expression. This value, if it's coming out to be 1 power infinity, then the value of this limit is basically e to the power limit x tends to a, g of x into f of x minus 1 is what you have. If you are getting anything, any undeterminate form in terms of powers, okay, if you have 0 by 0 or infinity by infinity, then it's clearly sorted out. Okay, then if you are getting anything in terms of things like 0 power 0, infinity by infinity, infinity power infinity, 0 power infinity, or infinity power 0, if you are getting these kind of things, then you can follow a procedure which is called 2L technique. Okay, 1L stands for logarithm and 1L stands for L'Hospital rule actually. Okay, so we'll see. If limit extends to a, f of x power g of x is of the form 0 power 0, infinity power 0, 0 power infinity. Okay, 0 power infinity. Clear? Then after say a infinity power infinity and so on. Okay, maybe some indeterminate forms in terms of powers. Indeterminate form in terms of powers. Okay, so indeterminate form in terms of powers. Then we follow the 2L procedure. So what this 2L procedure is basically, 1L stands for logarithm and the second L stands for L'Hospital rule. L'Hospital rule actually. Okay, so this is L'Hospital rule. Clear? So this is what you get. So 1L stands for logarithm and second L stands for second L. First L stands, second L stands for log L'Hospital rule. Like we'll work out an example which you can understand. See here. If you have, for example, a function of this form, limit x tends to basically infinity, x by e power x. Okay, this is coming up to be e power infinity form. So x power log x. Okay, so let's say this is infinity power infinity form. Yeah, x power log x, or log x power x, you say log x power x. Maybe simple, we'll deal this. Okay, so log x power x. So it's of the form clearly infinity power infinity. So what we'll do is basically we'll convert this into a form like this. Y is equal to, let y is equal to ln x power x. Okay, Now basically some function f of x power g of x. So you can see, first of all we'll apply the first L, which is logarithm, taking log on both sides. On both sides, this implies log y to the base e is equal to x times log of ln x. Okay, so or you take x power x. Okay, simple. Let's make the life simple. Maybe since we are at the beginning, so let's take x power x. Okay, then what is this value? X tends to infinity x power x. So this gives you infinity power infinity form. So x into ln x is what you get. So ln x into ln x is what you get. Okay, now let's apply the limit. So if you apply the limit, therefore limit x tends to 0 log y to the base e, because you are applying limit on both sides, is equal to limit x tends to 0 x into ln x is what you have. Okay, so x into ln x. Then let's see, since limit and log can be interchanged, okay, means if you calculate log of this function and then if you apply the limit, or if you apply the limit and then if you apply log, it doesn't matter. Like for example, you see, if I have limit x tends to 0 log x plus 2. Okay, so let's say you have this function, for example, you'll get some value. This value will be same as log of limit x tends to 0 x plus 2 to the base e. Okay, so this will be same, because you can see clearly, if you apply this function, if you put x equal to 0, this is log 2 to the base e. Similarly here, if you calculate log e of, you know, what's the number that come here, if you put x equal to 2, this is log 2 to the base e. Okay, so limit and this log can be swapped, because calculating log of the function and then taking the limit, or calculating limit first and then taking the log will never, in fact any mathematical operation will not change. Okay, so therefore I can swap this limit and log. So if I swap this limit and log, let's see, if I interchange this limit and log, you'll understand this gives me log of limit x tends to 0 y to the base e is equal to, okay, so to the base e is equal to, here is what you have, limit x tends to 0 x into log x is what you have. Okay, so x into log x. Now we can do one thing actually. So what is the difference in log and ln? Generally I'm always writing log y to the base e. Okay, yes, sure, applying ln on both sides. Maybe I'll write here so that you'll get much clarity. See, whenever I write ln, this means log x to the base e, because this is called the natural logarithm. Okay, so this ln stands for natural logarithm, and this is log x to the base e. This exponent is e. Of course people write loosely, but if you generally write log, okay, this means if I write log x to the base 10 is what this means. Okay, when you write log, this is basically defined as base to the 10, and if you write ln, this generally refers to the base as e. But sometimes in when people teach it, people generally loosely use this ln and log interchangeably, but they have the actual meanings. You can see in your gate calculator, for example, I have opened here, log e to the base e is 1, correct? So if I click e exponential, okay, so I have clicked this e, you can check, and if I click ln, my answer is 1, because it takes ln of this value, which means ln of e is log e to the base e is what it's calculating in the background and giving the answer as 1. But if you take e and if you take log, the answer is not 1. You can see this is basically log e to the base 10. So when you click log, it basically takes this base of 10. Okay, clear to all of you? Is this clear or not? So please type in the chat box. Did you understand the difference between ln and log? Yes or no? Yeah, please type in the chat box quick, a bit faster. Okay, now let's see. Now ultimately this is giving you of the form, so see here, this is giving the form 0 into infinity, of course minus infinity, so minus if you take outside, 0 into infinity is the form it's coming up. So whenever you have this multiplications 0 into infinity, how to get the tie result? Look, you want this value, first of all, let's say you want this value, limit, to proceed from here you first need this value, limit x tends to 0 x into ln x. So this is giving you 0 into infinity form, but you know the technique only for 0 by 0 or infinity by infinity. Okay, You know the technique only for these two. Okay, you don't know the technique for other things. So how to do this here? Let's check. In this case, you can see limit x tends to 0. I can slightly modify this as ln x divided by 1 by x. Of course, let's say this is infinity, x is tending to infinity. Okay, I have put x tends to infinity now. Okay, x tends to infinity, it will give infinity, of course. X tends to 0 is what we'll put, 0 power 0 form. Okay, please change that, x tends to 0. Clear? So please change this to 0, because infinity, obviously, you know, the functional value goes to infinity. That doesn't matter. A very big number power a very big number goes to infinity. So you can see this x power 0. Okay, x tends to 0, x power x. So it's giving you 0 power 0 form. That's what we are working. So let's see, when you put limit x tends to 0 ln x by 1 by x, it ultimately gives you, and of course this is plus what I mean, because the limit has to be defined always. Let's say we are putting a plus sign always altogether. So now because log has to be defined. Okay, now let's see limit x tends to 0 plus ln x by 1 by x. Now if you try to calculate this value, the value that you get is infinity by infinity. Means by making this small manipulation, like x into ln x is giving you the form 0 into infinity, but you know the things only for infinity by infinity or 0 by 0. So therefore you are trying to convert this function into a form of infinity by infinity or 0 by 0. You may have a doubt, if you put x equal to 0 plus log x gives minus infinity. I'll put a minus here and a minus here, then this minus log x gives me plus infinity, and this fellow also gives me plus infinity. Okay, I have exactly infinity by infinity form by adjusting this minus sign in and out. Okay, now let's see, this is of the form minus infinity by infinity. So minus limit x tends to 0. So since now I have infinity by infinity, if you differentiate, derivative of log x is minus log x is minus 1 by x. Derivative of 1 by x is minus 1 by x square. So this gives me minus limit x tends to 0 x is what you get. Okay, so limit x tends to 0 x, because if you simplify this, this minus 1 and minus 1 gets cancelled, this x cancels one time, so you have this x onto the top, and ultimately if you put x equal to 0, this value is 0. Okay, which means you can understand something, limit x tends to 0 plus x into ln x is coming up to be 0. Okay, this is what we have here. Okay, so x into ln x is equal to 0 is what you are getting here. Now in this range, x into log x is equal to 0, of course. So if you keep this value as 0, this implies log of limit x tends to 0 by to the base e is equal to 0 is what you're getting, because this limit is what we have calculated. So this calculation gave us the right hand side of this equation to be 0, which means you can see limit x tends to 0 y is equal to the log of something to the base e is equal to 0. So this quantity is equal to e power 0, because you know the definition of log, if x power n equal to a, log or if a power x is equal to n, log n to the base a is equal to x. Okay, simple logarithm definition. So this gives you e power 0, which is equal to 1. Therefore limit x tends to 0. What is y you have taken? Y is basically this y is equal to x power x. Okay, so what we have taken, y equal to x power x. That's why when you apply log, we have x into ln x. So limit x tends to 0, x power x is equal to 1. This is the result that you can find initially. X power x is equal to 1 is what. Okay, so this limit is 1. So when x is tending to 0, so in all determinate forms में confusion होता है, एक बार clear कीजिए. See, indeterminate form is basically where you cannot define the value. Okay, like 0 power 0 you cannot define. Okay, 0 power 0 is indeterminate form. 1 power infinity. Okay, then infinity power infinity, have things like this. Okay, or 0 power infinity, infinity power 0, all these things. Okay, so when you have this, you will work out, and the value is 1 basically here. So if you see, this value is 1. So basically whenever you have the power like this indeterminate form is giving you directly 0 power 0 form. So whenever you have anything of this form, anything of this indeterminate form, first L stands for logarithm. You apply the logarithm, then you'll generate some function, then you will apply L'Hospital rule in order to get the value of the function, and by using these two L's you'll calculate what is this limit. That's what I have told you in a short nutshell here. Okay, and if you plot this x power x, I'll show you in Desmos maybe. So x power x, x power x is what you have. So you can see at this value coming close to 0, I have defined this graph only for x tends to 0 plus, because log has to be defined. So negative side obviously there is no graph. So on right hand side, when x tends to 0 plus, you can see when x is coming close to 0, this function is coming close to 1. Okay, so you can see this is 0 comma 1 is what we are getting. Of course it's not exactly, but very close. It's like almost 0.9999 and it approaches 1. Okay, that's how you have the graph of x power x, and this graph tells you that as x tends to 0, y approaches 1. That's what we exactly found out from this calculation. Okay, so is this clear to all of you? Please type in the chat box yes or no. Clear to each and every one of you? Yes or no? Please type in the chat box. I'll have some water meanwhile. If you have any doubts at any point, please answer me, please ask me, or else everyone please type your response in the chat box. Only 2-3 are responding. What about others? Okay, so see here, I would like to give you a few more points which could help you in calculating a lot of limits. Okay, if in general, if you take any function, if limit x tends to a f of x, this is giving you 0, then this analysis what I have done is I have done with purpose. Whatever the function you take, okay, such that this limit x tends to a, this function first becomes 0, then limit x tends to a, f of x for f of x is always equal to 1. Okay, and please note this is not because 0 power 0 equal to 1. This is because of something different logic. Okay, so 0 power 0 is not equal to 1. 0 by infinity, indeterminate, no, 0 by infinity is 0 because it tells you 0 divided by a very large value will definitely give you 0. Clear? 0 by infinity is not indeterminate form. Okay, 0 divided by a big value, it approaches 0 totally. Okay, now let's see. Based on this, there are a lot of gate questions actually. Okay, so all the previous gate questions I would like to write. Limit x tends to infinity or x tends to 0, x power x. This is 1, which now we have seen. Just we have seen this value is 1. We have calculated. Similarly, limit x tends to 0, sin x or sin x. They have given this. Of course, this is also 1. This all these are previous gate questions. Okay, what I am writing. Limit x tends to pi by 2, cos x for cos x. This is again 1. Then they'll ask you a lot of things. Limit x tends to a, x minus a for x minus a. This is also 1. First. So whatever you do, this power will always give you 1. All these are previous year questions. Okay, sometimes they put a equal to 2, sometimes they put a equal to 3. Okay, then they put x tends to 0, tan x power tan x instead of sin x power sin x. Okay, they'll make the function such that when you put x tends to 0, this function becomes 0 and power of same function. Okay, that's what they give you. You can actually show this with the same logic of 2L procedure. Okay, and I would like to say one more thing actually which is important, of course. So let's see, let's take it up. Limit x tends to a or x tends to infinity, some function basically a naught x power n plus a1 x power n minus 1 and so on, a n minus 1 x plus a n plus f of x divided by this value divided by b naught x power m plus b1 x power m minus 1 and so on plus bm minus 1 times x plus bm plus g of x is equal to 0 if n is less than m, a naught by b naught if n equal to m, infinity if n greater than m, provided f of x comma g of x are finite valued functions. Finite valued functions. Okay, so these guys are finite valued functions. What's the meaning of finite valued functions? If x tending to 0, f of x power g of x is equal to same thing. Okay, so basically when the function matches. Okay, so if these two functions match, then in such case this is 1 if this is valid. Now let's see, these are finite valued functions. What is the meaning of finite valued functions? Means you can see sin x, cos x, sin x, cos x, maybe sin square x, sin 2x, cos 4x, whatever. So these kind of functions, if you see, whatever the values of x you keep, these functions will always have some finite value. Yes or no? Because whatever you keep between x, whatever you keep in place of x, sin square x always lies between 0 and 1. Sin x always lies between -1 and 1. Cos 2x always lies between -1 and 1. Okay, so you can check that these functions are basically finite valued functions. So whenever you have the finite value, then ultimately this is what it happens. Okay, so this limit will definitely give you one of these things depending on n. You can actually check this. It's not a very big story. So if you consider this limit x tends to infinity, a0 x power n, a1 x power n minus 1, a2 x power n minus 2. Okay, so and so on, a n minus 1 x plus an plus f of x. This value divided by b0 x power m plus b1 x power m minus 1 plus b2 x power m minus 2 and so on, plus bn minus m minus 1 x plus bm plus g of x. Okay, so you have this. Now whenever you have this, let's see, it's not very a tough job to do. This is equal to limit x tends to infinity. If I take x power n common in the numerator, I would get a0 plus a1 into 1 by x, correct? Because this is x power n minus 1, so x power n divided by x is what I can write. X power n, if I take common, I'll have 1 by x plus a2 1 by x whole square and so on, a n minus 1 1 by x whole power n minus 1 plus a n 1 by x whole power n. Okay, so 1 by x whole power n plus this function f of x into 1 by x power n. This is what you get. Okay, so this complete term divided by, if you take x power m common, the denominator, b0 plus b1 into 1 by x plus b2 times 1 by x whole square and so on, plus bm minus 1 1 by x whole power n minus m minus 1, of course. So m minus 1 plus bm 1 by x whole power m plus g of x into 1 by x whole power m is what we have. Okay, now try to understand one thing here. As x tends to infinity, 1 by x tends to which value? Can anyone tell me? If x is going towards very large value, 1 by x comes towards which particular value? What is the value that 1 by x will try to approach? Quick. If x is going very huge, then 1 by x goes to 0, right? Yeah, fantastic. This goes to 0. That means within this limit, therefore, limit x tends to infinity, when 1 by x is tending to 0, within this limit, when x is approaching to 0, this 1 by x goes to 0. Similarly, this 1 by x whole square goes to 0. All these are constants. Okay, so this goes to 0, this goes to 0, and similarly this goes to 0, this goes to 0, 0 and 0. Now if f of x is always a finite number, okay, I told this f of x and g of x are finite valued functions. Okay, if they are finite valued functions, that means this f of x gives you some fixed value and g of x also gives you some finite number. Since these are zeros, 0 into some finite number will be 0 and 0 into some finite number will be 0. If by chance, let's say you have tan x here, tan x can go to infinity and infinity into 0 will give you undeterminate form in this particular part. Okay, so that's why, because of infinity into 0 being indeterminate form, you cannot simplify this. That's the restriction I have put. F of x and g of x has to be finite valued functions. Okay, so in such case, this value comes up to be a0 by b0 into x power n divided by x power m. This is what you will get. Okay, because in this bracket starting from second term all terms are 0. Similarly here all terms are zeros. Okay, see basically what I have taken here, I have from this complete terms I have taken x power n outside. So if I take x power n out, x power n minus 1 can be written as x power n divided by x. So if this x power n is taken out, you will have this 1 by x remaining to the product of a1. That's what we have done. Okay, then this is what you have, a0 by b0 into limit x tends to 0, sorry infinity, x tends to infinity, x power n minus m, because x power n minus x power m gives you x power n minus m. Now try to understand one thing. If n is greater than m, okay, so if n is greater than m, then ultimately, or if n is less than m, let's say for example first, if n is less than m, because that's the first case I have written here when I'm writing the formulation, I have written n less than m. So if n is less than m, ultimately this power will become negative, correct? So n minus m is negative. So when you raise x power negative, then ultimately this is a very large number to the negative power. Okay, so a very large number to the negative power is nothing but 1 by, or basically some fraction divided by, like for example, you know, if I have x power minus 0.8, this can be written as 1 by x power 0.8, correct? You know this. So whenever this is negative and this number is very large, x tends to infinity, so this number is very large, ultimately this will go to 0, correct? Because the denominator will be very large, correct? Did you get this? If this exponent is negative, then ultimately for a very large value of x, this complete expression will die down to 0, correct? So can you all agree? Yes. So what we are telling is basically if x is a very large number and if you have the exponent to be negative, then ultimately the total value turns out to be, it approaches 0. Now when this approaches 0, so therefore if for m less than n, for n less than m, limit x tends to infinity, x power n minus m, this approaches, or this is equal to 0. Okay, because we have written the limit, we can put equal to sign. So this is 0. So in this case, when n is less than m, a0 by b0 is some constant. Okay, ratio of two numbers, it's just some constant. Constant into 0 gives 0. That's how we got this 0 if n is less than m. Clear? And similarly, if n is greater than m, it is infinity. For n equal to m, first of all, this x power 0 is 1. And if you see, there is nothing to apply on the limit, so ultimately it's 1. a0 by b0 is the value which you have. So using this result, if I ask you a question, something like limit x tends to infinity, x plus sin x by x minus cos x. If I ask you this question, ultimately because of this knowledge, you can say the answer is 1. That's it. Okay, because both powers are 1, so this is of equal power and these are finite valued functions. So this coefficient by this coefficient 1 by 1 is 1. That's all. Got it? Is this clear to all of you? Okay. Is this clear to you or not? And this result is very useful result. Okay, so anyway, in tomorrow's class I'll give you some more standard limits, but before I would like to give you some homework actually. So this is homework, please try this. Homework. In fact, tomorrow after giving the formulas, you can do these questions much easily. Okay, this question, yeah, you can do now, because you have understood a lot of limits actually. This will later maybe this some can homework. Fine, I'm giving 4 questions as homework, so please try these questions in tomorrow's class. I mean before tomorrow's class, and come for today's class. Of course, I'll delete the slides which I didn't give as homework. So you have got some nice questions. Okay, so these questions you can try as homework. And this question I have just answered, it is 1. X minus sin x by x plus cos x, the powers are same, so ratio of coefficients it is 1. Okay, clear? So with this we'll conclude today. Maybe I have brought more questions, but it's okay, the time is up, we'll do it in the next class. So in today's class we have basically drawn some graphs, some important graphs like x into sin x, then sin x by x, okay, then sin 1 by x you have seen, Then Signum function is what you have seen. Okay, then greatest integer function. And you know, guys, in recent years there were many questions from all this stuff. Okay, then we have worked out some limits, some nice limits, some L'Hospital techniques we have seen. Then we have also seen indeterminate forms in powers. Indeterminate forms in powers is what we have seen again. Okay, so indeterminate forms in powers, and then we have also looked at extending to infinity limits very much. Okay, so all these things we have seen. So when you will be conducting the doubt clearing class and also block matrix. Yeah, correct, right? I didn't teach this partition and 𝐂𝐤𝐬𝐞 theorem, correct? Okay, so in tomorrow's class, please remember me in the beginning of the class. Okay, so in matrices we'll see this 𝐂𝐤𝐬𝐞 theorem and also a bit of this partition or basically block matrix. Okay, we'll see this. Clear? Okay, so in the next class, please please make me remember in the first 5 minutes so that we can clear that. Then we'll go to the continuation of this calculus. Okay, clear? We still have many beautiful points about limits. We'll see in tomorrow's class, and then we'll slowly progress. Okay, yeah. So again, we'll continue the next class at 7 PM tomorrow. Okay, so on you know, tomorrow is Saturday, I guess. Yeah, we'll have a class tomorrow, and then we'll talk many more points about limits and all. Okay, so that's all from my side for today. I hope you all have understood the class. How about the Google form doubt clearing class? Yeah, I think on Saturday we have the class, right? I think see, you need not wait for that particular class of doubts clearing. You can always ask doubts at any point of time. Okay, no issue. Fine. I hope all of you have enjoyed a bit of colorful drawings today. Maybe in some graphs, this sin 1 by x, then sin x by x, this one, mod x, and all, of course, these things. And before this, we have solved some 1-2 questions. So I hope all of you have enjoyed a bit today. So we'll talk about another types. Fine. So thank you all. We'll meet tomorrow at 7 PM. Bye all of you.